Okay, so Dr. Johan, are you ready now? Okay, nice.
Yes.
So today, now we will have a second part of Dr. Johan lectures. Maybe now we will uh, listen about more advanced things about the MHD simulation. And I would like to remind you that we will have a quiz, right, for today's part. So be prepared.
Yes.
Yeah. Please, Dr. Johan.
Yes. Thank you very much, Ibnu. So let me start again my talk in this second part of this lecture. And I hope after break, then you already recovered yourself to listen for another uh, explanation about the solar MHD simulations. In the first part, I already uh, give you an explanation about the definition of magnetohydrodynamics and also the some of the basic MHD equations and the very useful concepts and parameters in MHD that usually people are concerned with. And this, in the second part, I will talk about the application of that MHD equations for solving the problems in solar physics. Okay, let me start again. Screen share. Okay, I hope you can see the slide now. Okay, so in this talk, first I will explain about the applicability of MHD in solar physics. So these are some typical scales in the sun. In the solar photosphere, we have temperature about 6,000 Kelvin and magnetic field strength is about 100 to 1,000 Gauss. The Larmor radius is very small, it's less than 1 centimeter, and the plasma beta is a little bit low, and the magnetic Reynolds number is also low. So if I mention about plasma beta and magnetic Reynolds number, so you have to be able to grasp what is the environment there. So if it means that if plasma beta low, then it means that the uh, magnetic pressure is more dominant than the plasma pressure. And if I mention about the Reynolds number is low, then it means that the diffusion term is important, something like that. So you should have an idea about what is the meaning of plasma beta and what's the meaning of magnetic Reynolds number. Because, well, we cannot explain in detail anytime we're talking about the corona and chromosphere or photosphere. So you already know that the plasma beta photosphere is something like this, and magnetic Reynolds number is something like this. And for corona, it's different. So we know that the plasma beta in photosphere is, well, this is not, actually this is not small. So we know that the plasma beta is the ratio between the plasma pressure and the magnetic pressure. So if the plasma beta value is 1, then it means that the plasma pressure and magnetic pressure is almost both equally important. If it's larger than 1, then we must consider that plasma is more dominant than the magnetic pressure. And for the magnetic Reynolds number, that if we have magnetic Reynolds number 1, then the advective term is almost equally important to the diffusive term, something like that. And that is for the photosphere, and for the corona, the temperature is much higher than in the photosphere. The temperature is about in the order of millions Kelvin, and the magnetic field is much lower than that, about in the order of unity or tens or even 100. So the Larmor radius is about 1 meter. And then we will show you in the previous slide, it's about 1 centimeter. So yeah, it's not bigger than 1 meter. And the plasma beta is very small. So it means that the magnetic pressure is more dominant. The magnetic Reynolds number is very big. It means that the advective term is more important, it's more dominant there. And the Alfvén wave, so I already mentioned about the meaning of Alfvén wave. Sorry, this is wrong. The unit is meter per second, of course, meter per second. So I will. So please correct this to the meter per second. This is the speed of an Alfvén wave, 10 to the 6 to 10 to the 7 meter per second. But the active region length is much higher than that. So yeah, not so much different. So it's about 10 to the 7 and 10 to the 8 meter. So the Alfvén wave to take for one active region is just about 10 seconds. But the flare time, usually if there's a flare, so the time is about 100 seconds to 1000 seconds, or about 10 minutes or something. So by knowing these typical scales of typical length in the sun, the radius and the Larmor radius, plasma beta, magnetic Reynolds number, Alfvén wave speed, and the active region length and the transit time. So we have some kind of a picture of what kind of MHD that we should use to simulate some activities in the sun. So I've showed you the definition of plasma beta, and here is the image taken from Gary 2001. We know this, the horizontal axis is the plasma beta, and the vertical axis is the height. And we can see that in the photosphere, here below the photosphere, we can see that the plasma beta is a little bit high here, larger than 1. And in the chromosphere and the corona, upper chromosphere and the low corona, the plasma beta is very low. And again, in the upper corona and the solar wind, the plasma beta is very high. So we can know that in solar wind, it has low density plasma and weak magnetic field. So we should have a very appropriate approach for this treatment of the solar wind. But for the corona, it has a low density plasma, but the plasma beta is very low. So dynamics of the magnetic field is dominant here. So even in the simulation, we can assume that the value of the plasma beta is just 0, or we call it 0 plasma beta simulation. And then in the chromosphere, the magnetic field and plasma motions are almost equally important here. The value is a little bit smaller than 1. But in the photosphere, it has a high density plasma, and plasma motions are dominant because the plasma beta here is higher, is bigger than 1. So why do we need numerical modeling and simulations, especially for the simulation in the sun? First, because of the limitations on the solar observations from Earth. We know that from ground observation, we can only observe the sun when the sun when the suns appear or can be seen from the Earth's surface, which means at the noon time. But at the night time, we cannot see the sun, so there's a limitation of time. We cannot observe the sun in 24 hours. But now people launched spacecrafts, and then they put that spacecraft in the orbits where they can observe the sun for 24 hours. But still, because the distance from the Earth and the sun is quite far, so we have still some limitations to the observations of the sun. And the second reason is because of the in situ observations of the suns are very difficult. You know, the sun is very hot, and of course, in the environment near the sun's situation is very harsh for the spacecraft to reach there. So yeah, it's very difficult to do in situ observations and then to send any probe there, and then you can calculate the or measure some parameters there. That's very difficult. That's why we need numerical modeling and simulation. And the third reason is to verify our understanding about solar physics. You know that in solar physics we have so many theories, and some people are bringing new theories now, but it's very difficult to examine whether that theory is true or not. So we need the numerical modeling and simulation. And because the laboratory experiments are sometimes more difficult than making a simulation, so people prefer to make a simulation and numerical modeling to test their theories and their understanding about some phenomena in the sun. Okay, let's recall again the basic MHD equation. We have continuity equation, equation of motion, energy equations, and ohmic law. And then we have induction equation, and then some constraints of the Ampere's law and the solenoidal condition, just divergence B equals 0. Then how can we use this? Of course, if we want to make a simulation, then we have to use some numerical technique, numerical modeling, but I think I don't need to explain that in detail here, because I believe that there's already several sessions that talking about numerical technique. You just can recall about that. But the idea is that the various numerical methods for hydrodynamics can be applied for magnetohydrodynamics. You already, maybe you already get some lessons about the difference method, how we can discretize any quantity in the analytical solution to the something like this. And then you also know about the time integration. So the easiest one, I think, by doing time integration, once you can discretize this equation, then you can just use the time integration. You can choose the Euros method, the leapfrog, or Runge-Kutta, or others. Or maybe you can use the finite difference, finite element, finite volume, or even for the advanced one, you can use a Riemann solver, and this is good for shockwave. We will not discuss about that here. But I can recommend you some or important or very good introductory books for this numerical methods. First one is a numerical method for fluid dynamics by Dale Darren. And the second one is the computational plasma physics by Toshiki Tajima. And this one is very good. So I learned a lot from this book about how to do numerical modeling and also MHD simulations. But I'm not endorsed by any of these publishers, but I think you can see this book, or you can learn from these books the basic concepts of the numerical methods and maybe the more detailed explanation about this. So I already mentioned about the MHD equation, basic MHD equations. But in MHD, usually people try to explain anything in two different frameworks. The first one is the ideal MHD, and the second one is non-ideal MHD. In ideal MHD, there is no resistive term exists, and therefore there is no diffusion. So I already mentioned about what's the meaning of diffusion and what is the meaning of ohmic dissipation. So ohmic dissipation or diffusion means that the magnetic field can interact each other, especially when the two opposite magnetic fields reconnect, and then some of the energy change to other forms of energy. Then that means that we have a resistive term. In ideal MHD, there is no resistive term. So the two elements of plasma, which are connected by the same magnetic field line, they will continually connected with the same field line for very, very long time. So there is no diffusion at all. So in this case, so magnetic flux is totally frozen in plasma. So wherever plasma moves, so magnetic flux will go following that plasma motions. So here we have a little bit different with the non-ideal MHD equations. So we have a little bit modifications here because we omit any of the resistive term. First one is this one. The resistive term means that this eta. This is the electric resistivity, and this is the magnetic diffusivity. We can omit this and this one, so it becomes like just continuity equation of motions, and the energy and the electric field can be defined like this, and the induction equations is only the advective term, and then we have the Ampere's law, and of course solenoidal conditions always become constraint for this. So what is the importance of ideal MHD? So if you are going to study about solar physics and about especially about the explosion and eruptive events, so you need to understand about the MHD equilibrium and MHD instabilities, because most of the explosions and eruption in the sun happen because of the loss of equilibrium, which means that the magnetic field or the plasma very quickly, abruptly explode, and then it will change its shape and the energy, just like solar flare and CME. So it's all related with the MHD instabilities. And because we have two different framework, which is the ideal MHD and non-ideal MHD instabilities, so we have now the ideal MHD instabilities. In solar corona, there are so many ideal MHD instabilities, but here I only show two of them, which is the helical kink instability and torus instability. So instability means that when the plasma or the magnetic field in the stable state, then any small perturbation will not change anything. You will not get any further change in the magnetic field lines or plasma motions because the system is stable. But if the system is unstable, that means that if you give a very small perturbation, then the magnetic field lines or magnetic flux will change dramatically, and then you can see a very different shape of magnetic field lines. The first one is the helical kink instability. just remember that this is ideal MHD instability, so there's no dissipation or diffusion. So this is just changing of shape. So the first one is the magnetic twist. There's some terminologies that I will use here, which is one is the magnetic twist. Magnetic twist is the winding of magnetic field lines around the probe axis. So how the magnetic field lines winding or turned. So when the twist exceeds a threshold, so instability can be triggered. So this is the meaning of the kink instability. So if you have a magnetic field line with plasma here, present in plasma magnetic field line, and then if the twist is very, very large, then it will become unstable. And people found that the minimum threshold for the helical kink instability is about 1.25 turns. So if the magnetic field lines twist for more than 1.25 turns, then the magnetic field lines become unstable, and then the helical kink instability will happen. And the second one is the torus instability. So you can imagine that if you have a magnetic flux tube like this is sunspot. Maybe you can connect this part of sunspot to this other part of sunspot pair. So we have a magnetic flux tube like this, and also you have a current, electric current here. So you know, if you have a electric current, ring current, so it will be unstable because of the Lorentz force. It will have a hook force that always try to make this ring current becomes expanding outward. So we need a strapping field which confine this magnetic field flux tube and also the plasma within it to be stable. So in an equilibrium state, hook force is stabilized by the presence of a strapping field. But if the strapping field becomes weaker too fast, then it will come to the critical threshold. With then we have another definition, so for decay index, and if this decay index for a flux source is greater than 1.5, then this magnetic flux will become unstable, and it will expand very quickly, and that's when the torus instability will occur. So these two instabilities are two examples of the ideal MHD instabilities. So there's no any ohmic dissipation or diffusions, but still the plasma and magnetic field will be unstable. And this kind of ideal MHD instabilities is very important for the plasma physics, especially for people who are working with plasma fusion, because well, actually they try to make confine plasma with a very high temperature for a very long time, so that the fusion reaction can realize there. So this kind of MHD instabilities, ideal MHD instabilities, are very important for that kind of study as well, and also in solar physics. And the second one is the non-ideal MHD, which means that the resistive terms exist, and therefore there's a diffusion by magnetic reconnection, and which means that the magnetic energy is transformed to other energies by ohmic dissipations. So here we have the magnetic terms, which means we have eta here, eta J here, and eta here in the induction equation, and also in the energy equations, where we can put another eta here. But anyway, maybe we can neglect this for in most cases. So So basically, the idea of non-ideal MHD is that we have resistive terms. So there is a diffusion in the system, in the plasma, then because of that, then the magnetic reconnection can occur. And because of the magnetic reconnection, then the magnetic structure or the flux drop becomes unstable, and then there's a solar flare happen. So basically, if we want to make a solar flare, then we need non-ideal MHD, because solar flare cannot happen only by ideal MHD. So we need a resistive term to make a solar flare, because solar flare basically in solar flare event, so the some of the energy, magnetic energy, transform to another form of energy. Here is the non-ideal MHD instabilities in solar corona. This is, I already showed you this image. This is the conceptual image of the standard flare model in 2D and in 3D. So basically, we have a magnetic flux arcade like this one, and then if there's something happen that will make magnetic reconnection to occur above this magnetic arcade, and then we have some kind of magnetic flux tube like this one with the filament within it, and then if there's a reconnection, then it will become unstable and it will be launched as a CME. So that's the basic concept of flare and CME. And then we'll have many features of the flare, like flare ribbons and also soft X-ray loops, prominence, and CME, and others. So in the non-ideal MHD instabilities in solar corona, the important thing is the magnetic reconnection that happen above the magnetic arcade, usually in the very high shared magnetic field lines above the magnetic arcade. Also, we have to consider about the divergence cleaning. So what is the meaning of divergence B cleaning? So this is divergence B. We know that from Maxwell equations, the divergence B equals 0, which is called a solenoidal condition or solenoidal constraint. And this solenoidal constraint is very difficult to achieve in the numerical modeling and simulation. So basically, you have to be careful in treating this part, because yeah, this part is almost independent from other equations in the numerical simulation. So you have to make sure, you have to check this one in your simulation, whether this constraint is still valid or not. So there are so many methods that you can do or you can apply to suppress this divergence B value. Some methods have been developed that can keep this value sufficiently small. One of the popular methods for this is the hyperbolic divergence cleaning method by Detner et al. 2002. So the idea is that you put some virtual potential here. Of course, this is not real, but yeah, you need this because you need to keep this constraint fulfilled. And then this is the virtual potential, and then the virtual potential should follow these equations. If you put this if you add this in your induction equation, then maybe you can suppress the value of divergence B. So this is the meaning of divergence B cleaning. So you must always check the value of divergence B. One method that you can just add all the divergence B in your system, integrate it in a volume, then you can see whether this divergence B uh, converges to a very small value or not. If you check this value and then you see that the divergence B is very big, even bigger than 1, then that's the problem. So you must very careful about this. So that's all the concepts and basic concepts and equations about the solar MHD. I hope you can grasp 1 or 2 ideas about solar MHD. At least you know what is solar MHD and what is the meaning of plasma beta, what's the meaning of magnetic Reynolds number, and what are the length scale, a typical length or and typical time and typical temperature in the sun and the solar corona and chromosphere and then the photosphere. So you can have an idea about which MHD framework you can use for your interest study. And yeah, maybe from now I will show you mostly just several examples or samples of MHD simulation in the sun. And for beginning, I will show you this case study. It's the solar flare in a zero beta MHD simulation. So zero beta means that the only important here is just the magnetic field. So we don't care about the plasma very much. So zero beta means that the plasma pressure, also the magnetic pressure is the only variable that is used in the simulation. So the first one to start with is the MHD equilibrium. So before we make the solar flare simulation, first we make the magnetic fields in the corona to be in equilibrium state or in stable state, so it doesn't move at all. How can we achieve this? There are so many ways for that. The simple one is by assuming that there is no force at all working on that magnetic field lines above the sun. In very small plasma beta and zero beta, so we assume that there's no non-magnetic forces and assume that the Lorentz force vanishes. Lorentz force finish means that the J cross P is equals 0. And of course, we have this constraint, divergence P also equals 0. And whereas J is the curl B. And then the solution we can get for this constraints are 3. The first one is the potential field. Potential field is very simple. So the curl B becomes 0, which means that there's no current at all here. Which means that if there's no current here, then the Lorentz force must be 0, right? If there's Lorentz force 0, then the magnetic field are stable. So the first one, we called it as a potential field, or because there's no current, we call it also as the current-free field. Here we get the solution, something like this. For example, we have here the positive region magnetic field and then the negative region magnetic field. If we connect this and we try to find solution for the potential field, we get a very simple shape of magnetic loops like this one. It's very symmetric and very simple like this one. So this is the most or the simplest form of magnetic fields that we can make by using this boundary condition. So it contains magnetic energy, but the lowest energy state. So if we have positive magnetic field region and the negative magnetic field region, and then what kind of magnetic field lines above this that you can make. The simplest one is the potential field. It will have the lowest minimum energy, which is this one, very simple. And the second one is we don't think that the current is absent there, so the curl B is not zero, but still it has some value. But here we can find the solution by using the linear force field. Well, I cannot explain in detail about this, but in this type of solution, you will get a more complicated shape of the magnetic field line. So it's not just very symmetric like this one, but it has some shearing motion. So you can see that the direction of the magnetic field lines here in the polarity inversion line is not just perpendicular, but it has some angle here. So this is the linear force free field. And the third one is the more realistic solution, which is the non-linear force free field. So the alpha here is not constant. So curl B equals to alpha B, and this is also the case for the linear force free field. But in the case of the linear force free field, the alpha is constant. For the case of the non-linear force free field, the alpha is not constant. And then we can get the more realistic shape of the magnetic field lines, because in the sun we can see that magnetic field lines is very complicated. So it's not just very simple like this. So it's very complicated like this. So by making this non-linear force free field as the initial state for the simulation, then you can get a more realistic result for your simulation. That's the first thing you must do if you want to make something like a solar flare simulation. So you first start with the MHD equilibrium state of coronal field. And then what next after you make the equilibrium state of the coronal field? Then, as I mentioned before, then you need a non-ideal MHD, because you need a resistive term there, because of course in solar flare there's a reconnection, magnetic reconnection, there's a diffusion there. So you have to have any idea of what kind of reconnection that you can make in your simulation. But there are several models for that, but the simplest one here is a tether cutting model. So here's the potential field, as I mentioned before. If we share this potential field, then we can get the more complicated form of magnetic field like this. So in this case, so you may have the magnetic field lines which has opposite direction here. And if there's a continuous motions of plasma in the photosphere, then this magnetic field lines with opposite direction can interact with each other, and then the reconnection can occur here. So this is the idea of tether cutting model. So you have eruption by magnetic reconnection because of the motions of this photosphere in the bottom of the surface of the sun as a trigger for the solar flare. And this is the conceptual image for the tether cutting model. You have, this is the onset before the onset of the solar flare, before the beginning of the solar flare. You have a magnetic field in an equilibrium state. You have prominence here inside the magnetic flux rope or magnetic arcade here. And then anyway that this magnetic field lines can interact with each other, and then there's reconnection around here, and then it will make a more elongated and more twisted flux rope here, and then it will become unstable, and then the eruption happen. So this is the idea of tether cutting model. So this is what we will use for the simulation. Well, this is the ensemble systematic simulation of flare trigger mechanism by adopting the tether cutting model. So we have in the beginning we have okay. So in the beginning we have a linear force-free field like this, but then there's some perturbation here, which makes this magnetic field become unstable, and there's some reconnection occur just above the perturbation field here. So in Kusano et al. 2012, they play around with this perturbation field here. So they impose small perturbation here. So I don't know if you can see the they impose some small perturbation here with different angle of orientation here, and then at certain angle, so eruption can happen, so reconnection can happen, and then solar flare can occur. This oops, sorry. Oh, sorry, there's a problem with the PowerPoint. Okay, let's wait for a while.
Okay. Dr. Johan,
Yes.
can we have a question?
Yes.
There is a question in YouTube from Muhammad Zamzam.
Yes.
I have a question. Which parts of the sun that can be treated as MHD or not? And the second one is, could you give me some phenomenon on the sun that relate to fan wave and magnetosonic wave?
Okay. So I don't know why this so there's problem with this PowerPoint. Sorry. So okay. While we are waiting for this, I will answer the question. First questions about the which part of the sun that we can use MHD for study, right?
Yeah.
Yeah, I think, well, basically we can use the MHD for almost all part of the sun, which means that especially for the photosphere part, we can use MHD, and also the solar corona also we can use MHD for that, also chromosphere and almost all part of the sun. But we need to be careful of the size of the or the typical length, because we know if we study the corona, we can study about the solar flare as a big picture, you know, just like this one, the simulation. But in some study, you have to study about the magnetic reconnection just in the region where the reconnection happened. And that part, maybe you need more than MHD. So you need the kinetic theory, because there's the length scale of your interest region is very small compared to the Larmor radius and the Debye length that I have already explained there. Maybe in several parts of the chromosphere and the corona, you need to have more knowledge about kinetic theories. So you cannot just apply MHD for everything by neglecting the aspect of kinetic theories in that part, because yeah, it very depends on the scale length of your interest region. That's the first question, I think. the answer is yeah. Basically, you can apply MHD for many parts of the sun, from the solar corona, solar chromosphere, photosphere, and also even the solar dynamo, which is the process that make the magnetic field is generated in the sun, and also determine the solar cycle. So you can also use MHD for that. And then the second question is about
About
sorry,
the Alpine wave and magnetosonic wave.
okay, so usually Alpine wave, they discuss about this Alpine wave when they are studying about the coronal heating. As I explained before, that the corona is much hotter than the photosphere and chromosphere. Why? There should be an explanation for that. So one of the mechanism for the coronal heating problem is that there's a wave that carry energy from the bottom of the chromosphere to the upper corona, and that is the magnetohydrodynamics wave, like Alfvén wave, and also magnetosonic wave. And also for the magnetosonic wave, we have in the sun phenomena called EUV wave or EIT wave or Morton wave. This is something like that some people call it tsunami in the sun. So if you have explosion in the sun, a solar flare, then we can see there's a ripple from the center of the eruption, which propagate through all direction in the sun, and it of course this is a wave, and you need to know about the magnetosonic wave there, because this is plasma and it's also in the highly magnetized environment, so there's a magnetosonic wave. So usually people treat EIT wave or EUV wave, or some people call it Morton wave, as magnetosonic waves. So I think that's all to answer
Okay.
the questions.
Yeah,
Sorry, I
thank
think I
you.
have to turn off this.
Yeah, please, you can do that.
Sorry, there's some technical problem here. Okay, sorry, my computer is frozen.
Do you need help? Maybe you can
Yeah,
share your presentation in Zoom and I will share screen.
yeah. Maybe that's a good idea.
Yeah.
Okay, that's good. Oh, I'm sorry, this is still not working. Do you already turn off the share screen? Hello, Ibnu?
I think. So can you share your presentation, maybe?
No, it's still freezing here.
Okay, so it's freezing. Maybe you need to restart the computer first.
Yeah, yeah,
Yeah,
maybe
we can wait for that.
I'm sorry for,
Okay, yeah.
sorry.
Hmm. So for the participants, if you have a question, maybe you can ask now. And then I would like to remind you that there will be the quiz for the last part of this lecture. The quiz will be given in Slack and Zoom. I mean the link of the quiz. So it will be around 15 minutes maybe. Okay, Pak Johan. Hello? Okay. So I think, okay, Dr.
Okay,
Johan
very
already with
sorry
us.
for the problem.
It's okay. So the committer will share the screen. Is it possible?
So you want to use the screen?
Yeah, I think the committer has a big up screen
Yes, yes, yes.
presentation. We can use it.
Okay, okay.
Yeah,
Um,
okay. You can have your
Yeah,
presentation now.
unfortunately, this one is the PDF one, I think, that I sent to the committee. But anyway, I am still opening my PowerPoint. So while we are waiting, I can explain in this backup slide. So here I already mentioned about this ensemble systematic simulation. So please forward. Okay, so in the previous one, I show the flare trigger simulation in the very simple coronal magnetic field, which is the linear force-free field. In the real condition, we have a very complicated structure like this. So we need more than just linear force-free field. And for that case, then we are making the more realistic initial condition, which is the nonlinear force-free field model. Here, then we use the data observation of the active region. This is active region 10930, and then we get the magnetogram data, and based on that magnetogram data, we can extrapolate the coronal magnetic field. So magnetogram data basically is just magnetic field in the photosphere, in the surface of the sun. But we want to know is the coronal field, coronal magnetic field, which is high above the photosphere. And once we have the coronal magnetic field, then we can do this similar ensemble simulation by changing the orientation of the perturbation. Like this, for example, we impose the artificial perturbation like this with direction like this or anything. So this is what we call as the data constraint simulation. So data constraint simulation means that we make a simulations, but we use a real data for as a constraint for our simulation. So it's just not a simulation that we can make any type of magnetic field or something. So this is based on the data, based on the observations. Next. So how can we make a non-enforced field extrapolation? So first we get this is sunspot from active region 10 and 30 in the upper image, and the bottom image we have the coronal magnetic field data. The white one shows the positive polarity and the black one shows the negative polarity, and then we have this is the vector field of the magnetic field here. And then we use the MHD relaxation method. Yeah, basically this is the same like MHD equations, but with some, as I showed before, we have a cleaning potential here, divergence B cleaning here, and then we also have the definition of the potential, virtual potential. So first we reconstruct potential field from BZ, and then we relax the magnetic fields toward the force-free state of the observed boundary condition. So I think I already can open my slide because we don't have an animation there.
So you want to share
Yeah.
your
Let me
slides now? Okay.
share my screen. Okay, I will go a little bit quickly for now. And this is the non-uniformity field results. The data that we use as a constant is the bottom part of the simulation box. And then we create the non-uniformity field, which is the extrapolation of the coronal field until we get the more realistic coronal magnetic field like this. And then we get the feature that is frequently seen in the pre-eruptive active region is a very highly shifted magnetic field like this, or we call it as a sigmoidal structure. And then we trigger the simulation and we use a reduced MHD equation. So basically we only need the induction equation like this. And then also we have to introduce anomalous resistivity to enhance magnetic reconnection. So this is commonly used in MHD simulations, especially for non-ideal MHD, because making natural magnetic reconnection in the simulation is very difficult. So we need a very, very high resolution for the simulations to realize the reconnection. So usually people introduce some anomalous resistivity, which is a very, very high resistivity in a very localized region, just to enhance the magnetic reconnection. So once we introduce this one and then we impose the virtual perturbance here, then the magnetic field lines here will reconnect, and then you can see the magnetic field lines, the original magnetic field lines look like this, but then it will reconnect, and then the more elongated twisted magnetic flux stroke will be created like this. And then we impose so many possible perturbance like this one, and then and then it's confirmed from the observations and simulation that opposite polarity type structure trigger X3.4 solar flare from this active region. Okay, so this is very much similar to the concept of the tether cutting model. So this the left one is the conceptual model, and then the right one is the simulation that we can recreate the model to be more realistic. So as I mentioned before, the aims of the simulation is to verify or to examine whether our conceptual model is valid or not. And then here in the first in the last part of my talk here, I will show some samples of solar MHD simulations and few aspects of solar MHD. It's because I have only very limited time now. So this is the example for the ideal MHD instability, which is the kink instability. I already mentioned about this before. And this is the study on how the twist and right of magnetic field in the solar corona affect the occurrence of kink instability. This is the simulation for from Torp and Klim in 2005. You can see this is the left part of this is the observations. I think maybe from Trace or something, spacecraft. And then we can see that the magnetic field lines really just look like the simulation. And it confirmed that some magnetic flux tube in the solar corona can erupt to become semi, while others are confined. This is the simulations. So if we have magnetic field lines which has a very strong twist, a very high twist, and then kink instability can happen. And this one is for the torus instability. This one is also for the ideal MHD simulation. So there's no reconnections that trigger the instability. It's study on how the magnetic field decays above an active region and its relation with the loss of equilibrium of a toroidal current ring. Because, as I've already explained before, that we can assume that the magnetic flux is just like a current ring, like this one, the toroidal current ring, but the shape is a little bit more difficult here, more complicated. But anyway, the concept is still the same. So in solar active region, the decay index is representing the decaying rate of the external magnetic field surrounding the flux drop in active region. So if the decay index is higher than some threshold, then we can make some eruption. This is from confirmed by the simulation like this one. This is by Inoue et al. In 2018. And also, this is interesting that Jiang et al. 2018, they tried to simulate the solar tornado, which is they claim that they observe this kind of phenomena in the sun. So this simulation of a highly twisted magnetic flux drop or sigmoid that was unstable and created a tornado-like eruption in the solar corona. You can see that at the beginning, it's very simple magnetic field lines, and then the very highly twisted magnetic flux drop can be realized, and then some eruption happen. And in the previous slide, I show you about the data constraint simulation. And this one is a little bit different. This one is data-driven simulations. So in the data constraint simulation, you only put some constraint in the beginning of the simulation, but in the data-driven simulation, so the bottom boundary condition are supplied with the stream of photospheric magnetogram data from SDO observation. So the observations data control the simulations time by time. So they supply the boundary conditions with the observational data. So this such kind of simulation is good for realistically producing a model of active region from its formation to eruption. And it's also useful for forecast in the future. For example, this is from Jiang et al. 2016. So they changed the boundary condition in the bottom of their simulation box. So for every, I don't remember, maybe 5 minutes or something with the observational data, and then they claim that they can make an eruption from that data-driven simulations. And this one is the prominence formations by Kaneko and Yokoyama in 2017. So they tried to explain how the formation of the prominence can happen in the sun. So they proposed the reconnection condensation model for solar prominence formations. And this is a little bit more difficult because they include the nonlinear thermal conduction and optically thin radiative cooling. And then they show that at the beginning, the magnetic fields are reconnected, and then because of that reconnection, then there's a condensation that will create a prominence inside the magnetic flux tube. Yeah, then the prominence or filaments are formed there. And then people try to make a very, very good simulation. They use just very well established neuron code here, which includes a realistic equation of state with partial ionization and radiative transfer along many ray directions. So this is the simulation of the deep underlying structure beneath the sunspot with the photosphere by Matthias Rempel in 2009. And you can see this is in a very high resolution simulation. They can simulate the formation of sunspots in very, very detail. It almost looks like a computer graphics. And this is also self-consistent radiative MHD. It is very advanced simulations, a comprehensive radiative magnetohydrodynamic simulations. and from solar subsurface to the upper chromosphere. And this is very very large system that they are trying to produce, and they also use very high resolution for that. So they use the extended version of the MURAM radiative MHD code 17, which includes coronal physics in terms of field aligned heat conduction and optically thin radiative loss. You can see that the simulation is very much mimicking the realistic dynamics of the corona by Cheung et al. 2018. Okay, so this I will come to the final part of my talk. So we already learned about different approaches that are needed for different conditions, plasma and magnetic fields in the sun. And we know that MHD simulation can be used as a tool to examine new theories and verify our understanding about solar physics. Reduced MHD equations are sometimes used in the simulation. So we don't use all the equations. Usually people just reduce that equation to the simplest one if they want. But of course, they should also have acceptable justification for that. And some artificial terms and adjustments are frequently used to accelerate simulation time in realized reconnection. As I mentioned before, the magnetic recognition is very difficult to be realized as a simulation. So there's some artificial, like artificial resistivity and artificial potential and others. So advanced solar image simulation include radiative transfer, thermal conduction, and equilibrium ionization equation of state. So not only hydrodynamics and electromagnetism, so they also include like thermodynamics. So you have all the combination of fluid dynamics and Maxwell's equations and also thermodynamics there, and then you can create a very advanced solar MHD simulations. Of course, that is very difficult. And there are many aspects and applications of solar MHD that are not covered in this lecture because of the limited time and maybe not in my capacity to explain all of this about waves, the coronal heating, solar dynamo turbulence, and others. Okay, so I will give you some concerns about MHD simulations. First is that once you can make a sufficiently advanced MHD simulations, so it will be easy to make another simulations just by playing with different variables. You can try for the different case or different variables or something, but yeah, be careful of this, because if you just making this, then maybe you will not find any new findings. So always try to find new methods to improve your simulations to be more realistic. And don't forget about the astrophysics or solar physics aspects of your simulations. And please remember that MHD simulations is a virtual laboratory to get new science, and so not for making a fancy image and videos. Okay, that's all. Thank you very much. So I recommend you for further readings if you like. So maybe you can download the slides that I already upload in the Google Drive. You can write this materials if you if you are interested. You can find, and then you can read these books and also papers if you are interested in MHD of the sun. Thank you very much.
Okay, thank you, Dr. Johan. Okay, for the last part, we have quiz, right?
Yes.
Yeah. Okay, so the communicator will give the link for the quiz in Zoom and in Slack. So please fill the question, and then maybe do you want to wait for the quiz, or we can go to the question and answer, because there is a question from the participant.
Yeah.
What do you think? Okay.
Wait. Yes. It's up to
Okay.
you.
Yeah, it's one question for Muhammad Zamzam again. I think he's with you now in Junjunan, I suppose. Okay. I have another questions. What is the computation cost to run potential field LFF and NLFF model? Do we need HPC? How about to run solar flare model?
Yes, yes, yes. So for the potential field is very simple. So you don't need a high performance computer or supercomputer for do that. So you can make a potential field in small computer. So it's maybe just need like several minutes if you know how to make yeah, you can optimize your code and then you can make the potential field in a small computer, maybe less than 1 hour. But for the linear force field, I think it's also not so difficult. You can make it also in the small computer, but for the non-linear force field, maybe you need a bigger capacity and maybe a high performance computer for that. And it will take, it depends on the code, but maybe some like the order of 1 hour or something. Yeah.
Oh, okay. So maybe in the future we can have a collaboration for the HPC.
Yeah, yeah, yeah. I hope so.
Okay. Okay, so for the quiz, is the community already give the link? Nah? Okay, I will check. It should be in Zoom normally. Ah yeah, in Slack also. Yeah, in Slack there is a Google Doc for the quiz. You can also click the link in Zoom comments.
Actually, the quiz is very easy.
Okay.
So
Yeah.
if you listen to my lecture, the first part and the second part, at least you know the idea of the how to answer the questions. Then it has
So,
nothing to do with calculation or something. So you just need to listen to my lecture, and
mm,
then maybe you can understand and you can answer that
mm.
two questions.
So there are two questions, right? Okay.
Yes.
Okay. So maybe I have another question for Dr. Johan. Yeah. Concerning the solar cycle, do you know what is the physics of it? I mean, the cycle is periodic, right? It's really clear. So, do
Yeah.
you know
Yeah.
what is the cause of it?
Yeah. People think that there's a mechanism in the interior of the sun which they call as a solar dynamo. A solar dynamo is what people believe that is responsible for the solar cycle. And there are many theories of solar dynamos, and the famous one is that there is at least two main motions in the interior of the sun, which is the alpha effect and also omega effect. So this both two mechanisms that work inside of the sun, which is responsible for the generation of the magnetic field in the sun and also the generation of the many solar phenomena, solar activities. So the idea is that we know that the inside of the sun there's some plasma motions there, and there's some like convections there, and this convections motions it will generate the magnetic field because it's a very conductive fluid, right? So if you have conductive fluid with some motions, then you may be able to create a magnetic field. And then it's also related with the transfer of the motions, transfer of mass from the pole of the sun to the equator of the sun, and so on. So this kind of dynamo motions that will finally create the or determine the length of this solar cycle. But actually, people are still trying to find which one is the main feature that is the most important one for determining the length of the source, the length and the height of the sunspot number in the maximum phase. So that is still a big questions. But yeah, there are so many complicated theories about this, and you can, if you are interested, you can go to find about the solar dynamo in Google, and you can find many papers discussing about that. So there's yes, several theories explaining about that. But the idea is that the plasma motion inside the interior of the sun that generate the magnetic field, but also the motion, they call it meridional flow, and also the rotational flow of the suns that will finally at the end determine the length of the solar scale as a solar cycle.
Okay. Yeah, thank you for the explanation.
You're welcome.
I think it's already 11 past 15, so uh, can just for the participant you can just fill the forms and submit it, and after that we can have a long break for the lunch. And oh yeah, before we have break we need to have a photo session maybe. Okay, so this the committee.
Okay, dear all participants, please open your camera. Sorry. Okay, please open your camera. We are going to take a picture.
Please open your camera.
Okay, ready all for first page. 1, 2, 3.
For Raditya, I think we still cannot hear you.
Test. Can you hear me? Hello?
Yeah, we cannot hear you yet.
Okay, for first page, yeah. 1, 2, 3.
Okay, it's good now.
Okay, again for second page. 1, 2, 3. Okay, last. 1, 2, 3. Okay, thank you.
Okay, thank you again, Dr. Johan, for nice talks. So see
I'm
you
sorry
again.
for the problem.
No, it's okay. It's normal because we are in online session, so sometimes like that. Yeah. Okay, so we will come back again in 1 o'clock, right? Okay. So have a bon appetit. Yeah.